So Cassandra is nothing but uh, just before going to Cassandra. So where actually the contents of Cassandra is stored, it's in data mantra. Training I have shared with everybody. In training you have Cassandra. Inside that you will find all the documents related to Cassandra. So this is the document you need to refer. Cassandra.txt, and all are the helping documents. Rest are the helping reference documents you can see. So we will see Cassandra architecture, Cassandra partitions, Cassandra database design, and how to choose a primary key, or choosing not primary key, choosing is called as partition key. That's important. How data model differs from normal RDBMS data model. So these are the things that we will be discussing about Cassandra. So first of all, Cassandra is a database. That's the first and foremost we need to know about. Cassandra is a distributed database. Distributed, we call it as NoSQL database. We know what it means by distributed. The data will not be restricted to only one system. You can distribute the data across multiple systems, and we can form a cluster of those systems. So Cassandra is a cluster-based database here. Just like Spark, we distribute the RDD. Here also the data will be distributed across multiple systems. You don't store one table's data in one system. A one table's data will be distributed across multiple systems. That's how you scale a database. The main reason of distributed processing is, or distributed storage is, you want to scale your system for more and more data. Now, what do we mean by NoSQL? Why Cassandra is called as, or most of the distributed systems are called as NoSQL database. The reason behind NoSQL database is what they consider is SQL means normalization. When you design a table, when you want to design a table, the very first rule you follow is that normalization. Your data has to be normalized. But in case of NoSQL, it is not normalized. We can call it as a denormalized. I mean, we don't specifically attempt to apply denormalization. We don't care here. Uh, uh, don't care about normalization. That's the reason They call it as a NoSQL database. They don't care about normalization. Here when we say normalization, what we'll have is we'll have a separate table for every entity. Like if we have like we have a employee details. Let's say we have employee details table. So usually we will have employee ID, name, then you have department ID. We will not have a department name here. We will have a department ID here, and department will be a separate table. There we will have department ID and department name. So that's the reason that we don't have redundant data. We, in case of normal RDBMS, we usually try to remove the redundant data, make it it is as compact as possible, make it as separate entity as possible. So there will be no redundancy, or we can say duplicate data. No duplicate data. But here, since there is no normal, since we don't care about normalization, there will be duplicate data. But it's okay because our cluster is a larger cluster now. It is not restricted to a single system. Our data is divided among systems, so there will be duplicate data. Redundancy will be there. It's better to say there will be redundant data. So that's the main thing about the SQL. Why do they call as a NoSQL and why do they call it as SQL? So Cassandra is a NoSQL database. It doesn't care about normalization, and hence there will be. We will see more when we understand the architecture. We'll see that how it is done. Now, since Cassandra is a distributed database, so there will be multiple systems. So this is our cluster. This I can say as our Cassandra cluster. We have system 1. We will call it as node 1, node 2, node 3, node 4. Each node is nothing but some IP address, and the IP address will be associated with each system. Now, how data is distributed among these systems? How data is distributed among these systems? Or before that, usually when we have a multiple system, just like let's say we have a HDFS, it is also a cluster. HDFS has also have a lot of systems here. But HDFS acts in the form of a client server model. One will be the controlling, there will be one controlling daemon running, and rest are all kind of a slave kind of a daemon which do the actual work. So we know that we have data node daemon running here, data node daemon running here, data node daemon running here, and we have one name node daemon running here. So we usually call it as a client server model or master slave model. You can best describe it as a master-slave model. There is one master and multiple slaves. Master do the arrangements, master do the controlling, master does the monitoring, master does all the control access, and the slaves do the actual work. But the problem with that is, or what we can say is not a problem, but that problem is solved. We can say it as a problem, and the problem is solved. There is a single point of failure. What we mean by single point of failure is, if the name node goes down, if that one system goes down, we cannot access the HDFS at all, even though all the other data node services are running. Probably let's say it is a 100 node cluster. Even though all the 99 systems are running and one system is down, that is the controlling system, you cannot access anything. So that's why we call it as a single point of failure. And single point of failure is usually solved using the zookeeper. We have already seen how zookeeper can be used for that. Most of the, if you take HDFS also in the same fashion, Yarn also is the same fashion. HBase also uses zookeeper. Most of the distributed master-slave model architecture frameworks uses zookeeper for its high availability. Now Cassandra is not a master-slave model. It is not a master-slave model. So there is nothing like a controlling system in Cassandra. It's nothing like one system will control, rest of the system will store the data. Nothing happens like that. Every system is a worker system here. Every system is just like a data nodes daemon, you can say. Just don't compare it with the HDFS because it is a database, that is HDFS. So every system is same. Every system stores the data. Every system controls or, or is responsible for its data. Nobody controls each system. Then how do they, if one of the system goes down, how things are maintained? I mean, there is sorry, since Cassandra is not a master slave model, there is no single point of failure. That's the good thing about Cassandra. There is no single point of failure. Then who knows about all the system? Who knows about, like here in HDFS we used to know that name node has all the metadata information where actually the data is stored, in which system the actual data is stored, where the blocks are stored. All that information is available to the name node in case of HDFS or in case of a master slave model. But here in Cassandra we know that there is no master slave model. Then how do they know the metadata of a particular system? So the way they work is they use a gossip protocol. Cassandra uses a gossip protocol to exchange information. Gossip itself says that they exchange information. They do gossip. So internally what happens here is every 1 second, one node will contact some randomly up to three nodes. Randomly up to three nodes. Let's say we have multiple nodes here. node 3, let's say node 4 here, node 5, node 6. So let's say node 6, node 7, node 8, something. Not so usually let's say we have a 8 node cluster. So internally what happens, each node will randomly choose up to 3 nodes and they exchange information with each other. The exchange information means what table information it contains. I said that Cassandra is a distributed database. A table data is not stored in one system. Table data is distributed among all the systems. So each system will discuss the information what part of the data it stores. They will gossip among each other. Like randomly node 1 may choose some randomly node 6 and node 7 and it will exchange the information about its data. So node 1 will say that I have such a tables that part of the data. Node 6 will tell that I have such tables that part of the data, and similarly node 7. Every 1 second, probably node 2 might be contacting node 1 and node 8. Node 6 may be contacting node 5 and node some 5, 4, something like this. So every 1 second, next 1 second, node 1 may contact node 2 and node 8. Some randomly, this is the second, next second. First second, second, so it will be contacting randomly. Now, node 1 knows the information about node 6 and node 7. Node 1 knows that. Now node 1 will exchange that information with node 8 and node 2. So it is doing a gossip. It is hearing from node 6 and node 7 and it is saying those information to node 8 and node 2. So that's how they exchange information. That's how they exchange information. Finally, what happens because of this gossip protocol, every node will know about every other node. Finally, every node will know about every other node. So every node has a metadata information we can see. Every node, because of this gossip protocol, every node has a metadata information about every other node. Hence, there is no single point of failure. Even if one node goes down, other nodes can serve that. Replication will be there, and metadata information is also will be there. Anybody can know that this node has gone down. This node's data is still available in some other node, and that is known to every node because replication will be there. If we have a data here, there will be a replication here, replication here, and that will be known to every node. If this node goes down, every other node knows that there is still data available in these nodes. So the client application can connect to node 5 and node 5 will know that node 1 is down, the data is still available here. Node 5 knows that because of the gossip protocol. So that's how they handle the high availability of Cassandra database. It does not require Zookeeper to have a high availability of a Cassandra database. Zookeeper is usually required wherever there exists a single point of failure, but here they use the gossip protocol to achieve high availability or to avoid single point of. There is no high availability. Here they avoid the single point of failure itself. So I hope you got the idea of how a Cassandra database. Right, every node acts as a server. Every node acts as a server. Some daemon process will be running. Cassandra daemon process. Now let's understand how data is divided inside a cluster. How data is divided among these systems. To understand how data is divided into these systems, so there is something called as a tokens. Cassandra depends on some token ID. So let's say usually earlier what used to happen is these token IDs were manually generated. Tokens were we'll understand this first because now it is automatically generated and it's slightly different. First we'll understand this to completely understand how data is distributed among the system. So you can Google. You can Google for Cassandra token calculator. It's down, I think. It's murmur hash calculator. This usually you have to open this Cassandra token calculator. It gives a good understanding. It is. I think that website is down. So as you can see here, for some value, this is this will not give a good understanding. Let me check whether this would have given a good understanding. This, but this website is down. Anyway, what we'll do is what happens is they will generate. Let's say we want to set up a 4 node cluster. We want to set up 4 node Cassandra cluster. So 4 tokens will be generated. Manually, if you go to that website, if you go to this website, there you will specify how many nodes you want. Then you just say murmur hash partitioner, and it will generate some 4 tokens. That 4 tokens are nothing but some huge value. Tokens are usually 128-bit values, which can represent a lot of data. So let me show the diagram here. So as you can see here, this is how a token will be generated. Manually, if you go to that website and you will say you want 4 tokens, you want to set up a 4 node cluster, so 4 tokens will be generated. Let's say these are those tokens. Node 1 is assigned this token number, node 2 is assigned this token number, node 3 is assigned token number 0, node 4 is assigned token number 4611. Now how does these node token numbers help us? So what it means here is from -9222, this token number plus one, not plus one, up to, yeah, from, oh, you are able to, Mohan, you are able to access that. I don't know, I'm not able to access from my system. It is not accessible. Can you once share your system? Shall I make you as a presenter for 1 minute? So you can share your system. Right. Right. So as you can see here, so Cassandra token calculator you can see here, and it is using Murmur 3 partitioner. We'll see what is that. So you need to specify number of tokens. I mean number of nodes. I said that we want to set up a 4 node cluster. So if we specify 4 here, so it will generate 4 tokens. You can click on the calculate tokens, Mohan. So as you can see here, it has generated 4 tokens. Each token will be assigned to one system. Each token is assigned to one system. Now what does that mean? I think that should be enough. Thanks, Mohan. So I will share my screen now. So we now assign that generated token to each system. Generated token to each system. So now what does that mean? It means that from this token number, there will be next token number will be 807. Next token number will be 806. I mean the whole number 807 minus 807 minus 806. The next token numbers. From that, from 808 up to 905. It will not include the last one. 905 will not, 4 will not be included. Minus 905 will be included. Up to this, all that data will be all the data associated with these tokens will be stored in node 2. So what I will do is, what I will say is, from 808 up to 905. All this data will be stored in this. We'll see how the data is associated with these tokens. These will be, I mean, each node is assigned one token, but there will be a next, all the sequence of tokens will be there. We'll see how those tokens are associated with the data. It is a sequence of tokens, a range of tokens we can say. It will be in a sequential order, and from here from here till here there will be a sequence of tokens. Right. So that's the reason I'm taking minus. It will be minus 809. So next token will be minus 9223372036854775809. That will be the next token. Similarly, next token will be 80, not 80, 810. Next token will be 811. All these tokens data will be stored in node 2. Similarly from 904 up to -1. Up to 0 means until -1. So that will be stored in, this data will be stored in node 3. Similarly from 0 to from 0 to uh, 903. 903 will be, this data will be stored here. Similarly, from 904 to 807, minus 807, it will be stored here. I think it should be 807 here, right? I mean, whatever. I mean, the main idea here is the token ranges data will be stored here. Now we did not say how a data or a record. Row database means we will say row or record. Row or record. How row or record is associated with token. That's important. How data or data here means row or a record is associated with the token. What is the relationship between the data and the token? We said that based on the token, the data is stored, or based on the token value, the rows are stored in a particular system. But this is how a token, whenever we want to set up a 5 node cluster, a 5 tokens will be generated. A 6 node cluster, we have to generate 6 tokens. As a result, again, each system will get a range of tokens. Each system will get a range of tokens, and your data will be associated with that range of tokens, and it will be stored in a system. So to understand that, let's take an example of a table now. Let's take an example of a table. Let's have a home alarm system. Now, what is a home alarm system? Let's say we have multiple homes here. We have multiple homes, and we are a company is installing a alarm system in that, or a security system. alarm system here. So a company is installing their device, which is kind of a security alarm system, where it will be sending the data to Cassandra database. They have their application, and their application is powered by Cassandra. They have their web application. So this their device that they have installed, they will be sending the data to Cassandra. So what data they will be sending? They will be sending the data like and anytime uh, somebody broke into the house, a burglar broke into the house, it will raise an alarm. So that alarm is kind of a event. That event will be sent to Cassandra to be stored. It will send a message to the owner of the house. It could send. That is also one more event that is being sent stored in Cassandra. Similarly, it can make a 911 call. From here, there may go a 911 call to the police station. Again, that is also one kind of an event that will be saved in Cassandra. Similarly, the house owner may set the alarm on or set the alarm off. The owner can turn on the alarm, or the owner can turn off the alarm. So even those events will be stored in the Cassandra. So something like alarm off event, alarm on event, 911 call event, somebody break breaked in event. Such events will be coming from every home. Let's say they have installed it in some 10 million house. They have installed this device on 10 million houses. Obviously, you will be getting the events from 10 million houses or 10 million devices. The events will be sent and the data will be stored in Cassandra. Now, when this data is stored in Cassandra, how the data is distributed? How the data is distributed? Whether all the data from this home will go to one system, or whether all the events from some three houses go to one system, how the data will be distributed. So that we have to see in the case of Cassandra. But this 10 million records, at one particular time you will be getting lot of events. I mean, it will be very rare. It is not a huge data here, not huge data, because you can see that once in a while the owner may turn on the alarm. Once in a while the owner may turn off the alarm. Once in a very rare case, a break-in may happen. Somebody may break into the house. So it's not that you will be continuously receiving the data. Once in a day you may get some 4 or 5 events with alarm off and alarm on. You may get at the max 2 or 3 events or 4 or 5 events per day from a particular house. So per day you may have some 50 million rows per day. On I'm taking the higher end here. Some of the house From some of the house there may not come any event at all. The owner might not turn off or turn on the alarm at all. So there may not be any events from half of the houses at all. So in that case, you may receive some only 10 million events or less than that also. You may have 5 million events rows per day. So not much of a data here. So you can that is what I'm trying to say is here not much data is coming, continuous throughput is not there, continuous data ingestion is not there, very less data we are getting here. Now the question arises how data these 50 million rows, how these 50 million rows are distributed among the node of a Cassandra cluster. So this is where you need to combine these things with the token, with the token. So first we need to create a table. Let's see how a table looks like. So there is a home.sql. You can open this. So this is how we create a key space. I mean database. We are saying we want to create a database. Our database name is home security. Simple strategy means your database will be on a single data center. If you want to have your database on multiple data centers, so there is some dynamic strategy we have to specify. And then we specify what is the replication factor. Usually the replication factor will be 3. We'll have a 3 copy of the data. But since I'm running on my single system, I will make it as a replication factor as well. Same like in anywhere else, how the replication factor is used, the same way replication factor is also used here for redundancy purpose or for failure purpose. We can copy this. What we'll do is first we need to start Cassandra. So if you go to the terminal, just type Cassandra. Just type Cassandra hyphen, give a space, then hyphen F. It will start your Cassandra server. So Cassandra server is up and running. So we have a Cassandra client. Just like we have MySQL server and MySQL client, we have a Cassandra client called as SQL from where you can give SQL kind of a query. So we are connected to the Cassandra cluster now, Cassandra server. So like we say, show databases, here we say describe key spaces. We already have our home security. What I will do is drop key space. Key spaces means database, home security. I'll just drop that home security database because we will create a new one now. The very first thing that we do is just copy this and paste it here. Create key space home security with replication equal to replication factor as 1. Now we can say same as use database, we say use home security. Now we'll create a table. So this is the table that we are creating, activity table. So this is home. As I said, every home has we have installed a device. Each device will have a home ID, and whenever an event is emitted from that device, there will be a timestamp. So this code used is when the owner of the house sets the alarm on or sets the alarm off, so the owner of the house has to use some code. So that is that code here. Event will specify what is the event, whether it is an alarm off event, whether it is an alarm on event, whether 911 call event, whether an SMS was made to the owner event, whether it is a burglar happened event, all those events. So to store such events, we need to create a table. We will discuss as same as we need to specify the primary key, and we are also having something called as a clustering key. We will discuss these two things. These two things are important here. We will discuss now. And these two things are associated. I mean, the primary key has two fields. So one of the field is where we do the association with the token that we have generated. So let's create this table. Just that we can trace it here. A table is created to usually in MySQL we say show tables. Here again we'll say describe tables. Describe tables, actually we have a activity table that we created now. We can just say select star from activity. So as of now there is nothing. We have home ID, date time, what was the code used to turn on or off alarm, and what actually the event was. As of now nothing is there. Now we have chosen what is the primary key. Primary key we have chosen as home ID and date time. Obviously we know that why primary key is used. Primary key is used to uniquely identify a row. So from a same home ID, from the same home you can get multiple events. Alarm off, alarm on, 911 call. It will be the same events. I mean, sorry, not same events. From the same home, we can get multiple events. But those multiple events will have a different timestamp. It may not happen on the same timestamp. It will happen on a different timestamp. Hence, hence, if we use the home ID as the primary key, it will not uniquely define a row. That's the reason we are using two columns as a primary key, which uniquely defines a row here. Home ID and the date time will give you one row. So that's how that's common in SQL also. But one thing we have to note about this is the primary key is divided into two columns. Our primary key is nothing but home ID and date time. Now, why home ID was chosen? Why home ID was chosen? Or before I say that, here inside the primary key, the very first column that you choose, this is always called as partition. Partition key is very important while designing a database. So this is very important. Partition key is important while designing a database. Now, what is a partition key? The designer, the database designer, has to choose which column is a partition key. They cannot randomly choose any column. So as you can see here, we have 4 columns. Home ID is one column, date time is one column, code used is one column, event is one more column. Why home ID was chosen as the partition key? So that question should arise. You cannot randomly choose any column as a partition key. There has to be some design principles we have to follow to choose a particular column as a partition key. We will come to that. We'll come to that. But let's assume as of now, by some means, we have chosen home ID as the partition. We some followed some design principles, let's assume, and then we have chosen home ID as the partition key. So partition key is used for partition key is associated with the tokens. Now we know that from which token to which token, we know that from from this token to this token, the data will be stored in some node 2. From some 904 to -1, it will be stored in node 3. Similarly, from 0 to 903, it will be stored in node. So how the data storage happens? So when you try to insert some data to this database now, we have set up a cluster, we have associated tokens to each cluster, we have created a database, we have created a table. Now it is turned to insert the data. Now it is turned to insert data. Let's say we do some insert into activity, home ID, date time, event, code used, and the values for that is these. Some values we have random values. So let's insert into this. So whenever I insert this data into which system it will get stored? Or you take the same to which system it will get stored here? Any idea on which system it will get stored? We have 4 systems here. We have 4 systems: system 1, system 2, system 3, and system 4. And we did insert a data into which system that row will get stored. So somewhere in one of the 4 nodes it should get stored. That row should get stored. In which node it will get stored? Not the min value. The way it works here is I said partition key is important, and we chose partition key is important. Home ID was the partition key. So what it does is, so if you remember how we calculated the tokens, the tokens were calculated using murmur 3 hash algorithm. It is just one hash algorithm. It will compute these tokens. It will generate these tokens. So this home ID value will be murmur hashed. It will take the home ID. and it will give out some token. It will output some token. So that token will be within these range. So it will be whatever 4 tokens we have, it will be one range of token. So the token belongs to, it will be inside one of these token. So then we will check to which token range it belongs. To which token range it belongs. Something like this. Like this. So as you can see here, whenever we insert the data, so it will compute a murmur hash on that home ID. It will output a token. After token is some random number. Hashing algorithm always returns some random number. Here in Cassandra, those random numbers are called as tokens. That's all. So that token, we will see to which range that token belongs. I mean, the Cassandra will see once the token is generated for that home ID, it will check to which range that token belong, and then the record will be stored in that token. Partition key. Just a second. Which right? So as you can see here, whenever we try to insert, let's say we try to insert this record. As soon as we try to insert that record, the Cassandra will internally compute a token for that partition key. For that home ID is our partition key. Home ID is this. It will compute this token using murmur 3 hash algorithm. They use the murmur 3 hash algorithm. It will get a token. Now where does token belong to? So it comes in between this number and this number. Anything in between these two numbers will be stored in this system. So that means that this record will be stored in the system. That row or that record is stored in that system. Similarly, again we get one more token. Again we get some event from some other home, some home ID 551, home ID 551. Again a murmur will be computed, and it will check to which, it will get the token, and it will check to which token range that belongs to. Based on that, it will be stored in some other system. So we can see that. So there are different tokens generated. Different tokens generated. So we can see that. So some the second token was generated and it comes in this range, hence it will be stored in this. This will be stored in this. And the third token, if you see 943, which got we got the token generated as this. This comes in the range in these two, hence it will be stored here. So this is stored in node 2, this is stored is node 3, this is stored in, sorry, node 1, 2, 3, 4, node 4. So I hope, I hope you got the understanding of how a node is stored. How a row is stored inside a particular system in the Cassandra cluster. It all depends on the partition key. It all depends on the partition key, which is our home ID. We chose home ID as our partition key. So what indirectly it says. Here is a question. The question is, the gossip interval is always 1 second. Usually, yes, it is by default 1 second. I think that is also configurable, but by default it is 1 second. We can mention it in the Cassandra configuration file. We will see the Cassandra configuration file, but even I haven't seen the gossip protocol configuration parameter there, but I think we can specify. I will just Google and let you know. So this is how the data is stored in Cassandra. So this is how the data is stored based on what is the token ID. So indirectly what it says here is, if you get one more event from this home ID, we can get multiple events from a particular home, right? We can get alarm turn on, we can get alarm turn off, we can get some 911 call event. Multiple events we can get from the same home ID. What it means here is all the events coming from, because in that case home ID will be same. Even though we get multiple events from the same home, in that case home ID will be same. As a result, the token will be same. Murmur hash will give the same token for the same input. As a result, all the events from the same home will go to same system, or we can say same partition. So all the records will with the same from the same home will go to same system. It will not be distributed. So that's the key point to remember. Here is a question: does it balance or replicate the data to other nodes after record gets stored in one server? Right, it will be copied to another server. If we are specifying 3 replication, the data will be copied to another server. So if we have a data, so actual data, this data is stored here, then it will be replication 1 will be here, uh, and the next replication will be, so data will be replicated in other 2 systems.
The question is the same keys, the range of keys will be stored in the particular server only, or it will be copied to other servers?
Sorry, can you come again?
Actually we are storing based on the key, right?
Oh, home ID.
The token number.
Based
the token.
on the number, right?
Yeah, token number. So the range of token numbers will be stored only to the particular node, or it will be copied later. It will be copied to other nodes.
later whether it will be copied to other nodes. So, I mean, what's the problem statement? What could happen? I mean, what is the intention behind the question?
The intention is like so. Suppose we are maintaining a table, we will be storing the records over the multiple nodes
Correct,
based on the tokens.
correct.
So, if some of the node gets some problem or something, it's goes down. So
Okay.
we may not get the range of keys from other nodes, right?
Okay. When you say replication, so this token information will also be there in the replication.
Okay. The
So
replication happens in some other node or within the server nodes.
no, this is the original copy. I can say this is replication one, this is replication
Okay.
two, this is replication three. It happens in three different nodes.
Okay.
So if this node is down, we still have the data available here replicated.
Okay.
So internally it will know
Okay.
that the token will be associated.
Mhm.
So every node knows that this particular data is available here also and here also.
Okay. Okay.
So it will work internally. We don't have to take care of this externally. All these things are taken based on the token itself.
Okay. So here there is no master slave kind of thing.
No,
So
nothing.
everyone is a master.
Right. Everyone is a master and everyone is a slave, we can say. That happens because of the gossip protocol. It will know that from this token range to this token range, the data will be stored in some node. Every node will know that. So that's how the data is stored. And choosing the home ID as the partition key is crucial because based on that only the data will be stored. The data will be distributed. Data is distributed, and again all the records from the same system. So it happens in this fashion. We have multiple homes here. We have home 1, we have home 2, we have home 3, we have home 4. Some multiple homes are there here. We have our Cassandra cluster here. So all the events from a particular home will be stored in one system. The events from this home will not be distributed among the cluster because we have chosen home ID as the partition key. Because all the records with the same home will get the same token number on doing the murmur hash, hence it will go to the same system, or we can say it as a partition. All the events from a particular home is treated as one partition because home ID is chosen as the partition key. All the events with the same home ID is treated as one partition. All the events from here may also go to this system because its token range may also fall here. Its token range may also fall here. So in that case, and this all the records, all the events from this home may go to this system. All the events from here may go to this system based on what is the token range. Some other home is there, some other home is there. All the events some may go here. Some one more home is there. All the events means what I'm trying to say here, a particular home's data is not distributed among the clusters, but overall the data is distributed. Here is a question: what if the system goes down? That's what I was trying. If the system goes down, there will be always a replication. You will you will store it in some other system. You will always store some in other systems. No, it doesn't let me whether it stores in other system or it will hold on to that system. Let me check on that, Leela. So either there are two possibilities. I'm not sure on that. Now here is you can store it. Original copy. This is the original copy. This is duplicate copy. This is the replication duplicate copy. Either it will update to the duplicate copy or or the way actually things work. We have multiple systems here. So some you are having a web client from which you are inserting the data. Web application you have, we connect to this application client. You may connect to any one of the node. Just like we have a bootstrap server, something like a bootstrap server will be configured in your web application through which you will connect to one of the application, to one of the node. So you insert data from here. You insert the data here. Now whatever we insert, this is node 1, node 2, node 3, node 4, node 5, node 6, node 7, node 8. You inserted them some home data. That data belonged to a system node 7. It belonged to system node 7 because the token was in this range. The token range was handled by node 7. So obviously from here the data should go to node 7 because node 3 knows that. Every node knows about every other node's token ranges. So node 3 will send that data to node 7. If in that particular time, if node 7 is down, the data will be stored in node 3 itself. The data will be stored in this node itself. It will make a note that this data belongs to node 7. Now as soon as the node 7 is brought up, then it will be stored. That's how the data is stored. If that node is down. Temporarily, node 3 will accumulate the data for that node because it knows that that's the token. It knows what token range the node 7 handles. I hope, Leela, that was clear. Uh, Leela, if you are talking, your voice is not audible. I see that your mic is on, but your voice is not audible. No, it's still not audible. I assume that it was clear, or if you have a question, you can message again. Meanwhile, I will take the second question. Suppose the primary key, that is home ID, only one value. So in this case, also home ID is treated as a. I didn't understand the question, Ravi. Can you explain me a bit? Okay, you are saying there may be hundreds of records, but you have only one value for home ID.
Actually, in the script, you mentioned that primary key is home ID and date description. So suppose there is no date description, only one value. Primary key is home ID.
Okay, okay.
So
Thus,
yeah,
in that case also, home ID is treated as the partition key. Sorry, I misinterpreted
okay,
the question wrongly. Right, in that
yeah,
case
that's
also, home ID will be treated as the partition key.
okay. Got it.
Okay, what happens to the token key? Nothing happens. Here is the question. The question is, since this system is down, since this system is down, what happens to the token key assigned token number that is assigned to that server? That number still remains there itself. Only thing is, you cannot write to that system now. Any data that belongs to that token range now, you cannot write it unless the admin person goes and restart that system. It will not work. So till then, the data will be stored in some other system, some other application. Some one more client may get connected to system 8. That client will also insert some data, and that data may also belong to node 7. Since node 7 is still down, again it will be part of the node 8 only. Node 8 will store that temporarily. As soon as it comes up, as soon as this comes up, so every node will start writing the data there. They will send that data which belong to node 7 to node 7. So I think that your intention of the question was whether that token will be assigned to some other node. It will not be assigned to some other node. It will not be assigned to some other node. It will be that node itself, and temporarily other nodes will be holding the data on behalf of node 7. And as soon as the admin person restarts that machine, and as soon as it is up, every node will come to know that that node is up. Then they will start writing to that node. So that's how the data distribution works. So I was telling about what is the indirect implication. Because of that partition ID, what was the indirect implication of that partition key? Home ID we chose as a partition key. The indirect implication is that all the records from the same home will be stored in one system, and that is called as one partition. This is one partition. This is one more partition. All the records coming from this home ID is one partition. This is one partition. Here again we have two partitions. Again we can have one more home. From that home also we can get the data here. We have three partitions here. So that all the records for a particular partition key is treated as one partition here. So we are having three partition. As of now, there are three partition in node 2. Node 1 has two partitions. Here we have node 4. This is node 3. There is one partition here, one partition, two partitions here, three partitions here. The data is divided. The data is perfectly divided across all these systems. But again, all the records from the same home will be in the same system. So that is actually the design principle. The actual design principle is that making all the records from the same home to be stored in the same system. That we have to do. It did not happen indirectly actually. As a developer, as a database designer, we have explicitly chosen in that way. We have explicitly said that put all the events from a particular home in one system. That's the reason we chose home ID as a partition key. So the reason behind that is whenever you give the query, the question arises. The main thing we consider when we design a table or a database in NoSQL databases or just like Cassandra, you don't design your database based on entity diagram. If you remember, in RDBMS we usually use entity diagram where you normalize your data, where you normalize your table and create multiple tables. Here we don't create the table based on normalization. We create the table based on your access pattern. So whenever you are designing a table, the team has to sit together and they have to come up with what type of queries you will be giving. Access pattern means what queries the clients will be giving. So based on these queries, a table is designed. It is not designed on the normalization way. It is designed on what queries the clients will be giving. So here the most of the queries that we want to give here is most of the queries that we want to give here is select events from particular home on a particular day, because the whenever the burglar happens, the police or the police might need to know on that particular day what all events did happen. So the police would also want to know select events from particular home in last 2 days, what all events. So similarly, last 3 weeks, something like this. Last 1 month, what are all the events that we received that happened in particular home. So these are the queries that the client want to give. The client wants to give all these queries. Select events from a particular day, from a particular home, from a particular uh, home, what was the last 2 days events, from a particular home, what was the last 1 week events, from a particular home, what was the last 1 month's events, how many times burglar happened. So in last 1 year, what was the events from a particular home. So such type of query the clients want to give. So to if that is the client's, if such type of queries the client is expecting, in that case we have to choose the partition key in such a manner that whenever the query is given, you fetch all those records from a single system. You should not have a query which will go through all the systems and get the data. Your query should you should design your database in such a way that whenever a query is given, that query should get the data from a single system. Now when I give this query, When I give this query, select events from a particular home. Let's say I say select star from activity table where where home ID equal to some h some 155 something. So when I give this query, how much system will be from how many systems the data will be fetched? How many systems the data will be fetched? The data will be fetched from only one system, because we know that all the events from a particular home will be stored in only one system. We are not going through all the system from the cluster and getting the data. Let's say this is 155 system. This is 155 home ID. All the records for this home ID will be available in only node 1. All the records or all the rows will not be distributed among different nodes. It will be available in only one node. That makes Cassandra read fast. That's how they achieve the faster read. So that is the thumb rule we have to follow. The thumb rule is, whenever we are giving a query, you should design your table in such a way that all the rows for that query should belong to one system, or all the records, all the rows should be fetched from a single system. And because of that, we chose home ID as the partition key. Because only if you choose home ID as the partition key, then all the records with the same home ID will be placed in one system. Otherwise the records will be distributed in a random fashion. So I hope you got the idea. On the idea is the design of the designing table is on access pattern. Access pattern means what all queries you are going to give. So let's say our query is select events from a particular home. We want to do some analytics or aggregations on each home, on the particular home. So you will usually give the queries on that particular home, in which case you want to have all the rows for that particular query to be available on a single system, not on different system. So based on that, you design your, you choose your partition key. You choose your partition key. So I hope you got the idea of how you choose the partition key. Let's say for example, as of now, what we are having, let's say as of now what we are having is, home ID, we have date time, we have code used, then we have actual event. Let's say we also have area code here, or area. In Bangalore we have or we'll say city. Instead of area, we'll say city. We also have one more column, city, and let's say cities are Bangalore, Hyderabad, we have Chennai, we have Mumbai, we have Pune, we have Delhi. Many. Uh, let's. There is a question here. Replication is done due to gossip protocol, and we have data across all other servers. No, uh, I don't think so. Data is replicated due to gossip protocol. That is internally handled. We don't. it internally copies the data from one system to another system, or whether it does through, I don't think so it does through gossip protocol. Through gossip protocol, it will come to know that from this token range to this token range, some data exists in the a particular node. Gossip protocol is usually used to uh, gossip the metadata information among all the nodes. It may not be used to copy the data. Or let me check whether it piggy banks copying of the data. I don't think so. It does piggy bank. Let me check on that again. So your idea is the idea is whether it piggy banks or not, right? Along with the gossiping, whether it piggy banks the data also. Let me check on that. So let's assume that we have home ID, we have date time, we have code used, we have event, we have city also. We have one more column called city. Now, now, now most of the queries that clients give is select events from city Bangalore. Select events from city Chennai for last 1 week. Similarly, select events from Delhi for last, what all events happened in the last 1 month. How many burglars did happen in Delhi for the last 1 month? Let's say these are all our queries. I mean, the client is expecting such type of queries to be given. So in such a case, how you will design your database, or how you will design your table, and what will be partition key here. Because our main idea about designing the database is, or designing the tables is, we have to choose a partition key. So obviously now, correct, that's correct. City will be, you have to create one more table now. The same table you cannot use. So let's say you are having this queries also, and you are having the other query also. You are having both. Your client expects these queries also. Select events from a particular home. Select events from a particular home from the last 2 days. Select events from a particular city also. From a particular city uh, from the last 2 days. So you, in that case, you have to have two different table now. Table one, table one will have home ID as the partition key. For queries related to particular home. So you will create one more table, table 2. Now city will be the partition. So this is what I was saying. You don't, in Cassandra database or in NoSQL database, they don't care about the normalization. Data will be redundant. Here also the data is redundant. I mean, if you see, the data is redundant here. They don't care about the redundancy here, or normalization. Here we can say that data is denormalized. It is not normalized at all. The idea behind that is whenever you give a query, that query should fetch the data in such a way that all the rows belonging to that query should come from a single system. So that we can make only happen the way we choose our partition key. So we create one more table and we say partition key as city. So in that case, what will happen is all the records, all the records belonging to Bangalore city will be stored in one partition, that is in one node. All the rows belonging to Hyderabad city will belong to one partition or one node. So the query will be, the data will be fetched from only one system. That will make your Cassandra much faster. So I hope you got to understand how the databases are designed in in NoSQL databases. It is based on your access pattern. You have to sit and come up with all the access patterns. Based on that, you start designing your table, or you start choosing your partition key and you start designing your table. So I hope the things were clear on how you design a database in Cassandra. Right, right. Yeah, here is a question. The question is, we used order by while creating the table. So we only talked about the partition key because that's the key to your database design. We only talked about partition key. But along with that partition key, so when we created the table along with this partition key, we also had one more column, and that column we are saying with clustering, with clustering. So what it says here is date time is the clustering key, home ID is the partition key, and date time is the clustering key. Now clustering key always says how a data or a record is ordered inside a partition, how a record is sorted inside a partition. So as I said that there is multiple home here. This is one home. I have one more home. So I have one more. I will just take three homes here, and we have a cluster, Cassandra cluster. So I have one system here, one more system here, and one more. Let's say multiple systems are there. So let's say the data from this home is stored in this node. Data from, so we can have multiple records from this. One was alarm off. We have a partition. This we call as a one partition. Let's say the record from here also, this we call as one partition. This is a partition also. Now the clustering key says how rows are sorted in, how rows are sorted within a partition. That is said by the clustering key. We have said our clustering key as date time. Our clustering key as a date time. Hence, the records inside the partition will be sorted based on the time. And how we are saying, we want to sort it in the descending order. We want to sort it in the descending order. So clustering key always says that how rows are sorted within a partition. That's the meaning of clustering key. And it could be sorted in ascending or descending. By default it is ascending order, but here we are saying our record should be sorted within the partition in the descending order. So the most recent events will be on the top. The most recent events will be top, and that helps us to get all the records in the past one day, get all the rows in the past two 2 days, get all the rows in the past 1 week, If you have such a query, this is the type of query we are looking for, past 1 month. So it will be in the ascending order of your, it will be, the data is in the descending order of your timestamp. Hence, all this data will be together. If you are asking for last 1 day of data, it will be together. You just have to fetch the data from that. Can we define sorting based on other field which is not part of the primary key? I think so, but not sure. I should check on that. I will check on that. For what I guess is, or what I think is, it should be on the key itself. It should be on the key itself. Non keys may not be used for sorting, because once you sort it, right, it I think it will be on the clustering key itself, because clustering key itself defines how the data are sorted within a partition. There is no other way to sort within a partition. It has to be through the clustering key itself. So whatever you choose as a clustering key, that will be used for sorting, because the definition itself says that. What if more than two fields are in? You are saying, what if there are more than two fields in the clustering key? That's the question, right? Because here we are having more than. So then we have to. So it we have to choose on these keys only. If there is one more field, then I think we have to say how it has to be sorted. So it has to be, I think, part of the key itself. Part of the key. Non-keys, I think we cannot. Even if we have more than two fields here, probably we have to choose on these things. Let's say there is one more called as something else also. Sort on something. Some I don't know what will be now. So probably date is by default we are saying date time as the clustering key. I mean, here we are not saying anything. Here, if we have anything here, ABC, it only says that ABC, home ID, date time, and ABC are used to uniquely represent a row. But here we are not saying that ABC is the clustering key. We are only saying that date time is the clustering key, so it will be sorted on the date time. So I think if we include that also, ABC here, so then it will be part of the clustering key, and then the sorting will be based on that again within each partition. But again, I need to, I will just be more sure on that, and I will let you know. So so for these such type of queries we are having, select the events from particular home for past 1 day, select the queries from particular home for the past 2 days, select the queries from a particular home for past 1 week. So when we give such a query, we know that we have sorted the data in the descending order of the timestamp. The past 1 day's data will be here. Probably past 2 days data will be here. Past 1 week's data may be here. So we have to just scan from this range to this range. That's all. It will be stored in a continuous fashion on the disk. On the disk, it will be stored in a continuous fashion, not randomly somewhere else. So that fetching of the data becomes much faster. So that's the reason we have the clustering key and the partition key. How fast it is possible to read the data from the cluster. So that's our design pattern, how we used to design a Cassandra database. Whenever we are writing to the based on the murmur hash. So earlier they used to use hash partitioner. Again, both are same. Murmur 3 hash. Now they are using murmur 3 hash partitioner. Earlier they were using some standard hash partitioner. So only difference is both will give out you some token, some random numbers. You give some input to a hash algorithm, it will just give you some random number, irrespective of whether it is a hash partition or murmur 3 hash partition. The only difference is murmur is faster, because whenever you are writing the data, every time we are computing the hash for that particular row. So when we are computing the hash for that particular row, you have to compute the hash. You have to compute the hash, so it will take time, because every record we are computing the time. Sorry, for every record we are computing the hash, which will take the time. So we want to make that time as minimum as possible. So murmur 3 is much faster. It computes the hashing. That algorithm is faster. It gives out the random number much faster than the hash partition. So they want to achieve a write also at a faster rate. Write should also be faster, not only the read, write should also be the faster. So murmur hash adds its contribution to increase the speed, adds its contribution to increase the speed. But there is no some one more way to increase the speed as well, that we will discuss tomorrow. How to how actually the write happens on Cassandra, we will see that. So I hope the things were clear here on Cassandra. So we'll wind up the session here, and let's continue tomorrow same time.